And this has really important implications. And this is what I'll show you in the demo here in a second. So what it means is that allowed transitions are either Garada to Ungarada or Ungarada to Garada. And if we think about the kinds of orbitals we have access to in a metal, or in an element, you could say in general, right? We have s orbitals, p orbitals, d orbitals, and maybe f orbitals. And so what is the symmetry with respect to inversion of an s orbital? If it had an inversion center, would it be Garada, which means it's symmetric, or would it be Ungarada? Garada, right? Because if you take a sphere and you invert it, it looks exactly the same, right? But if you look at a p orbital, I'm drawing little orbitals next to the letters here, right? What's that? If you invert it, the two signs switch, right? It becomes its mirror image. It becomes the inverse of itself. It's Ungarada, okay? D orbitals, all of them, doesn't matter which one you pick, but they have lobes that look like this, okay? It's Garada. And f orbitals are crazy looking, but I'll just tell you it's Ungarada, okay? They alternate, G, U, G, U, okay? So what this means is that you're allowed to have, say, a D to a P transition, right? Or an S to a P transition. But you're not allowed to have a D to a D transition, which is super important to us right now, okay? Doesn't matter what orbital you started at, you're not allowed to go to another D orbital by this rule, okay? So that means that in our complexes, which we've carefully mapped out, E2G and EG, for example, right? This is not allowed. But yet, this color that we're seeing right here in all these, I'll pick an aqua complex here, right? This pale pink color we're seeing here, and this is reasonably, I didn't measure it, but I dumped a good bit of cobalt chloride in here. This is reasonably concentrated. We're seeing a forbidden transition. Okay? This is not allowed by the spectroscopic rules. And actually, I mean, it's not allowed by physics. We cannot see this, okay? But we are, and it's because this is not happening in a cold vacuum. Okay? What's happening is, as we are, as light is coming in, there are also vibrations being excited in this molecule, and those vibrations temporarily break the symmetry. Okay, so it was this perfect Garada, or it was the perfect Garada d orbital, but as it vibrates, the shape distorts. We can see it only when it's distorted in the right way. Okay, so a fraction of the time we're seeing it happen, and that's really what this.
Sorry.
No problem. I'm surprised I'm not coughing myself. I'm quite ill. I'm just totally dosed up on medicine right now. I'm going to be a mess in an hour. So Beer's law, right, it has to do with it lets you calculate this molar absorptivity coefficient. I mentioned this before, but you could say that this is a measure of the fraction of time, or the fraction of events under which a photon of light is absorbed. And so it's extremely unlikely that the photon is hitting this at the exact right moment, that it's vibrating in exactly the right way that it needs to break this symmetry. So this is this rule is broken. Some fancy way of saying that is it's broken due to vibronic coupling. The vibrational modes are coupled to the excitation modes, and that allows you to see this. So most transition metal complexes have very pale colors like this, right? But there are times when you can have a transition metal complex that has a super intense color. I'm using language that I try to avoid, right? Because the MO diagram is just an MO diagram. There is no longer a metal and a ligand. It's just a mix of orbital energies, right? But if we kind of go back to what this diagram looked like, right? We had all these d orbitals, and we had, like, let's say a bunch of 6 different ligand orbitals. We'll call this, we have to actually include like this pi donor or pi acceptor orbitals down here, right? We found that a whole bunch of these get occupied. Down here, there's a whole bunch of occupied orbitals, right? And then up here, we get our sort of classic, T2G and EG. And that these orbital energies move around depending on this bonding or anti-bonding combination. But there are a bunch of electrons down here, and they could potentially get transferred up into unoccupied orbitals up here, right? These orbitals may have Ungerada symmetry, right? We know these are Gerada. We have been writing this little letter G the whole time, right? They're Gerada orbitals for an octahedral complex. But for orbitals that may be due to pi donor, I don't know that I have those particular slides with me here, but I bet I can pull one up in the book real quick here. There's one important transition here, which is, so these are the mixing, these are the symmetries of these pi donor or pi acceptor orbitals. And so you include the T2G here, which alters your sort of ground state term. It can push it down or up depending on whether this is a donor or acceptor. This is drawn as an acceptor up here. But there's also T1U, which mixes with the p orbital here. Okay? And so that ends up forming a bonding orbital down here. And this is always occupied. And it's generally the highest occupied molecular orbital right below what we're filling with our d electrons. Okay? So there's an extremely likely transition between this T1U orbital and these G orbitals, like these T2G or EG, so varies. And so these transitions then will be allowed by the Laporte rule. And so they tend to be very intense. Okay? And so this is given a special name, which bothered me for a long time. Okay? It's called charge transfer bands. Charge transfer means that in principle you're transferring charge from one thing to another, right? And in this case, we're imagining that it's transferring the charge from the ligand to the metal. That's the excitation we're doing, right? And there's two kinds. There's ligand to metal charge transfer, which is very common. LMCT. And so this would be from occupied, always filled here, T1U orbitals, which are somewhere below the T2G orbitals from a pi donor. And we excite them into, maybe partially filled or something T2G orbital. Okay? And it's this gap right here that we would see in color. And so this is now Ungerada to Gerada, so it's Laporte allowed. And so that means the quantum efficiency, the number of photons, the fraction of photons that are absorbed is way higher. So the color is very intense. So generally the organic, or the inorganic dyes, the paints, the old pigments, are all based on this kind of transition. And that even includes things that are, well, for example, a cadmium sulfide is cadmium yellow. It's a classic pigment. I don't know if any of you have ever bought paints in like, Michael's or Hobby Lobby or something, right? But they have all these names that have metals in them. The old lead paints, lead chloride, lead iodide, those have very intense colors also. And they all are based on this kind of transition, this Laporte allowed transition. They're also generally tetrahedral complexes, which means they never were G or U, but the d orbitals still retain some aspect of that, I guess, in their bonding. Yeah, anyway, it is always more intense when you have these transitions from these p orbital based ground states to these excited states. Yes.
Is that the case for like permanganate as well?
Yeah, permanganate then is it's a pi donor, it's an oxide ligand, right? And then O4 is a pi donor. It's also tetrahedral, right? So it messes everything up. But it is the transition we see, that dark purple color, is coming from that oxide. It's from the. It's not T1U because it's different. It's tetrahedral, but it's coming from one of these ligand-based orbitals to the what used to be the metal orbitals.
What shape is like titanium dioxide? Usually,
So that one is in the crystal structure. It's octahedral, but it's white, right?
Yeah.
Which means it's scattering light. It's actually probably transparent, but we're seeing tiny crystals. So when we don't see a color and it looks white, it means that we've ground it up and it's just scattering light everywhere, right? But it is absorbing like crazy. It's just absorbing in the UV. So that's type, well, actually, okay, so there's a couple things going on. First of all, that's a D0 compound, okay? Titanium 4+, started with 4 electrons, it has none now, right? So there's no electrons in this region that can transfer. So that means it won't even have a pale color because it's those D to D transitions, this stuff, that is causing these pale colors to be observed. There are oxide ligands, but the bonding in that thing is super strong, so everything is pushed way down, and so it absorbs really strongly in the UV, just outside the visible region. We don't see it. Okay, So anyway, let me show you an example of this ligand-to-metal charge transfer. I also have one other example of, it's already turning colors, interesting. So this is 2 different iron salts. This is iron 3 chloride and iron 2 chloride. I just did that. This is pale green in solution, and once you add water to it, it begins to oxidize in air. It oxidizes anyway. So this is beginning to turn a little bit orange because I mixed it up this morning and it's already beginning to oxidize. But it was pale green. It's again the reflection of the spectrochemical series, same idea as what we saw before. But the iron 3 chloride, I'm going to add a ligand to it. And that ligand is thiocyanate. Okay, so if I have FeCl3, again, it's not really FeCl3 once it's in solution. It's really iron, it's an aqua iron 3 chloride. Okay, and the chloride doesn't matter here. It's outer field. It's outer. This is the outer coordination sphere. This is the inner coordination sphere. We're going to add to it thiocyanate. It's one of the ligands we've been talking about. This almost always bonds through the sulfur. It's rare that it will preferentially bind through the nitrogen. Sulfur is a better donor of electrons, all that stuff. Right? The bond is going to tend to be stronger. So what we're going to get is an iron thiocyanate complex. And this is another really classic complex. This is in a bunch of like these chemistry magic shows. We'll see why. I'll just do it up here, I think. Try not to make a mess. This is particularly super toxic. So I'll just take a drop of this thiocyanate here. 2 drops. There we go. Right. It makes this, I don't know if you can tell, that's super dark red. It looks black, okay? But it's basically, it's like bloody iron and all this stuff. They have all these names for this magic trick, right? Water to wine, you know, because if you dilute it, it looks like red wine. But it is effectively the color of blood, because blood is an iron complex with a porphyrin ring, which is a good pi acceptor. It's a different transition that we're seeing in that, but it's, again, a very, very intense color. And I show this not for the color change necessarily. Oops. Find my iron. Oh, well, my iron I just destroyed, but it was slightly orange, as you recall. More or less sort of this pale color here, right? And just the intensity of color, right? The molar absorptivity. I didn't change the concentration, right? It is dramatically different, right? So what I did was I went from a weak field ligand, which is itself a pi donor, but we don't see that we now see this ligand to metal charge transfer band. We're seeing this kind of transition now taking over. At least it's moved into the visible range. So this has become small enough now that it's moved into the visible range. This looks red, and so it must be absorbing in the green. It's possible that this one here, the orbitals were too far away. They were maybe not split enough for them to be close enough to the d orbitals for us to see it. The transition is allowed somewhere. It's very intense, but it's probably in UV. So anyway, my point is, anytime you see these very intense colors of metal complexes, you're likely to see what are called charge transfer events. Okay? So this one is quite common, ligand to metal charge transfer. This happens with pi donors only. So we see this with things like chloride, we see it with thiocyanate. It's relatively common, even oxide with permanganate, right? So we mentioned KMnO4. The classic salts are like lead chloride or cadmium sulfide, very, very bright colors. Those are all pi donors. So the other one is metal to ligand charge transfer. And so it's MLCT, metal to ligand charge transfer. If you're starting with metal centers, maybe T2G orbitals, maybe EG orbitals, and we're going up to something which is allowed, probably another one of those T1Us. And again, I'll take you back to this little MO diagram here. This one is drawn for pi acceptors because you see there's empty orbitals up here. So here's our perhaps filled orbitals with from the transition metal, the T2G and the EG. This will have N electrons, however many we started with. And up here, there's a T1U orbital. There's an A1G here, that doesn't do us any good. That's a G to G transition, still no good. But there is a T1U up here. And so we can excite from either of these up into this unfilled T1G orbital. And that transition, if it's in, well, I mean, no matter what, it will be very intense. That's now Laporte allowed, parity allowed. So this works for pi acceptors into empty T1 orbitals. So these aren't as common. There is a very important in research dye, ruthenium, it's bipyridine ruthenium, rubibi it's called. I think it's probably 2+, maybe 3+. It's electrochemically active, so it's both. But bipyridine is a pi acceptor. This is a very, very intense dye, and it can be complexed in with other things. You can derivatize this bipyridine, and it's basically used as a little electrochemical probe of reactions. But since it's a pi acceptor, it exhibits this metal to ligand charge transfer there. So anyway, these are two ways to break the first of our two spectroscopic rules, which is the Laporte rule. But generally, transitions between, if I summarize here, generally, D to D transitions are weak. Okay, meaning their molar absorptivity, epsilon, is low. They're stronger when for tetrahedral complexes. And for tetrahedral complexes, the reason is because there is no G or U. It has no center of symmetry. These are non-centrosymmetric structures. And it's very strong. They're no longer really D to D transitions, but very strong transitions are observed for charge transfer. Okay. So let's talk about the second rule, which is really never broken. This one is broken quite often, always really, a little bit. But the second rule is called the spin selection rule. And it's written as transitions between states of different spin multiplicities are forbidden. But it's basically you can't flip your spin over during a transition. So essentially what it means is if we had maybe a D6 compound, the only transition that's allowed is this one, which is a different spin. This would be the excited state here, right? And interestingly, if you have something like a D5 high spin compound, these will be almost completely clear. Because there is no transition possible. These are all of aligned spins. That is Hund's rules applied here. This would be the highest multiplicity state you could have, so there is no transition possible in that particular complex for a D to D transition. So this will have almost no color. That would be a manganese 2 salt. I don't have one with me, but they're super duper pale greenish color, but almost white. Very different from, say, an iron salt, which is just its neighbor. Even an iron 2 chloride salt is a much brighter color because it has this allowed transition. So essentially, this is the transition that I didn't bring here today, but I meant to, is iron 2 chloride.
Oh, wait, wouldn't iron 3 also be D5?
Iron 3 is D5. Iron 3 is D5, but iron 2, yeah, okay. So you're asking about iron 3. Yeah,
like, because iron 3 tends to be pretty intense, right?
It tends to be pretty intense. Yeah. Iron 3. So that tells me that perhaps that orange color that we're seeing is indeed a charge transfer event.
Oh, okay.
It is pretty bright in color. So that would be this, it's a pi donor, right? So we're seeing that T1U orbital transitioning up because none of the D to D transitions are allowed.
Okay, yeah, because I guess well, iron 3 chloride is really intense, but like iron 3 nitrate is pretty pale.
True, but those would be iron 3 nitrate in water should basically be the same as iron 3 chloride in water.
It's not. It's like, well, iron 3 nitrate in water is kind of a pale peachy color, whereas the iron 3 chloride is a really intense yellow color.
All right,
So
so
that's
in this
probably the
case, what we're
chloride
probably seeing is then in
ligand.
equilibrium, if there's chloride around, it's occasionally bound to your metal, and so it's adding to the total bonding, right? It's altering the orbital energy, so we're probably seeing a penta-aqua chloro complex and all these things rapidly exchanging. Hey, we're getting a little off topic, but yes.
Okay, sorry, I was
There's
just
some
trying to wrap my
differences.
head around that. Yeah.
Right. They tend to be the same color, it's just the intensity may change.
Right.
So maybe you're activating those charge transfer transitions. Okay. So anyway, the spin transition rule is almost never broken. It is possible to have cases where it is broken, not so much in metal complexes, but you've all toyed with these glow-in-the-dark stickers and things, right? To expose them to bright light, and then maybe several minutes later, it's still glowing, right? This kind of pale, weird greenish color. And that's an event you may have talked about in spectroscopy somewhere called intersystem crossing, where you have, I'm drawing d orbitals here, but it doesn't matter, right? You have some maybe filled states here, and then you had an electron that transitioned up into an excited state. And when it got up there, it looked like this. And everything would be fine. This could pop back down, but it goes through some sort of relaxation event before it transitions back down, where it flips over. Okay? This is coupled to some kind of vibrational energy. There's something weird happened to it, okay? Because this doesn't just naturally happen, but it had a mechanism to transition, maybe coupling through another bond or something to another spin. And now this is not allowed. When it's not allowed, it's kinetically, you could say, very slow. It takes a long time for the vibrations to couple in just the right way for this to break this rule, because it doesn't really break the rule, it does something else. Okay? And so as you heat up these glow-in-the-dark things, they decay more rapidly, so they emit brighter color for less time, all that stuff. So that's phosphorescence. It's a delayed reaction caused by this rule being enacted. It's not broken. It's just, if you can flip the spin over, it's like a singlet to triplet transition or something like this, they call it, right? Then you can, you see these sort of strange effects. But we're never going to break that rule for these transition metal complexes. Okay, so let's get busy. Finally, I've set us up. Let's get these huge handouts that I made. This is like the one time in this entire course that we can be quantitative. Just bring out our calculator. That's really exciting. Okay, so this is messy enough that I wanted little slides for a moment. I want to try to draw this. Okay, let's talk about this first line here. This is a big mess. So we spent the whole beginning of this chapter. Let me get rid of this slide behind this. We spent the whole beginning of this chapter dealing with this side right here. Okay. So a D2 configuration, we worked last time. I intended to have this be in all one lecture. But if you look back to our D2 configuration, our ground state we said was a triplet F. Just believe me for now. Okay. The excited states are all the other letters in some order that is very hard to predict. Okay. So we said for our free ion term, somehow we have a maximum angular momentum of SPDF3, right? M sub L is 3 max. The spin is positive. What is it? It's positive 1 max, right? The two electrons are aligned in their spin, either together or opposed or whatever it is. And yeah, so that's what happens in the absence of a field. Okay. As we begin to build an octahedral complex in this case, for an octahedron, there's a different diagram. You'll see it's related for a tetrahedron. All of these terms split. Okay, in the same way that our d orbitals, when we put them in an octahedral field, split into different groups. Okay, it's based on group theory. And we've not dealt with f orbitals before, but we have dealt with d orbitals. And so you see this d term here splits into e, g, and t2g. These are now spectroscopic terms. These aren't molecular orbitals anymore. But these are the symmetries now of these spectroscopic terms in this field. It's very strange. So what we call this F term splits into these three groups, and the exact groups aren't important to us. We don't care whether they're H2G or T2G or whatever, but it splits into three of them. It happens to be T1G, T2G, and A2G, and these come from the octahedral character table. They come from that same thing. There are rules on how to split terms, and they are basically mirroring the rules for how to split molecular orbitals. And in fact, the atomic orbitals, it's all, as I said, backwards. It was named for these, so they're one and the same, right? We're seeing evidence of the orbitals. Okay, so this triplet F term splits into three parts. This higher energy D term splits into two parts, et cetera, all the way up. The multiplicities are retained. So if it was a triplet before, that means our spins are additive, they're aligned, at least some of the time. And so all of these are triplets. If it was a singlet before, that means the spins were opposed, right? That cancels out. They only had a maximum M sub s of 0. Then they're all singlets. So we know our ground state is a triplet. The spin rule, which we just talked about, says that you can't flip your spins around. So if you start as a triplet, that means that your spins are aligned. They have to remain that way, right? So your only excited states possible are other triplets. You could go up to here. You could go, and actually, if you draw what triplet P means and triplet F means, once you start splitting the terms out, the triplet F term will split into things that look like this. Up here, we have these excited states, which look like this. Okay? And so this looks like a single one of these electrons has transitioned up. So we call this T2G squared, which means it's two different T2Gs. Right? We call this T2G EG, which is 1 and 1. And up here is EG squared, which is two different EG orbitals. So on the very opposite side of this diagram, it's really hard to tell what's happening in the middle, but on the very opposite side, these sets of terms right here, interestingly, mathematically, are what happen if you take the characters for T2G, and you just look it up on the character table. The E identity operation, for example, is 3 because it's a T term. It's triply degenerate, right? The C4 term, which would be next on this octahedral character table, is something. I don't remember what it is. Maybe it's 1, okay? So you take those numbers and you square them all, and then you reduce that again, okay? So you take all those numbers, you reduce it, you get this set of things. If you just mathematically do that operation, this is the result of T2G squared. This is the result of T2G times EG. If you multiply all the numbers together, you get this, right? And then if you take EG and you multiply it together, you get these. Okay, and this thing that we're looking at right now is called a correlation diagram. It's going from one extreme, which is our atom outside of a field, just the bare atom, just what we get if we just look at 5 degenerate d orbitals and figure out what its ground state is, just like we've been doing, right? D2. We figure out our ground state is, this and all the excited states and these other things. The other end is what happens if we take our completely split diagram, which we already know about. It's based on these T2G and EG orbitals occupied in different ways, and we connect the dots, okay? We connect the lines. And so you'll find that there is always the same symbols on the left side and the right side of this. When you split the F term out mathematically, like just the d orbitals split into this EG, T2G, there's another set of rules on how F goes. You'll find that all these letters are copied over here, and you just connect them, making sure that you never cross the same symbol with itself, and that's the only rule, okay? So the T1G, there's more than one of these. So here's another triplet T1G, and we have to make sure that we don't switch these. Like we don't connect this one up here and that one down there, right? We don't ever have to do this ourselves. This is all done for us. There are lines that cross, but they aren't the same symbol. So you just go across in the only way you can. There's exactly one answer to this little puzzle, connecting the lines across. And you have to know the relative energies of these terms. This looks like an excited state. This looks like a ground state. This is all done. This has all been calculated for us and then confirmed with spectroscopy and all that. So what this x-axis means on this plot is basically the strength of your field. So it goes from a 0 field at all. This is the free ion term, which is no octahedral field at all the way up to like an infinite field. This would be like a perfectly infinite field where EG is like infinitely far away from T2G. And our real systems are somewhere in between those two. And the transitions we see are basically between the lines that are spinned allowed. And those are the bold lines on this diagram, okay? Because I've drawn bold lines everywhere there is a triplet state. And I've labeled them. From the ground state, which is, it turns out, the triplet T1G. That's the one that connects the bottommost triplet states. The second allowed transition, the second allowed state would be this triplet T2G one, right? But weirdly, in the infinite field, there are 2 different terms that represent this, okay? works out that way. One is a T1G and one is a T2G. There's another transition just above that one, or maybe it would come first if you're a very weak field, which would be a triplet T1G, and et cetera. So, you know, if you look at the entire UV vis spectrum of this D2 compound, you would find 1, 2, 3 different peaks at 3 different energies. Or maybe if you were really unlucky, you'd be right here and you'd see 1, 2 peaks, and that second peak would be 2 terms on top of each other. But this y-axis here is the energy of transitions that are allowed. And it's these energies that we're about to try to figure out. But this would be impossible to use because everything is sloped. I mean, it wouldn't be impossible. We like lines. we like things that come from an x-axis which is flat, not curved. Okay. So let me just kind of walk you through these other slides. This is the written version of what I just said, but let's make sure that we hammer this in here. So on the left side, that's the free ion terms over here. They split in a field similar to the splitting of orbitals. So a D term has a maximum L of 2, similar to D orbitals with a lowercase l of 2. And so they follow the same mathematical rules. And so they turn into capital M sub L values of 2, 1, 0, 2, and they split into the G and T2G terms. Yeah, and then I mentioned also that on the right side, what we do is square the orbitals. The characters. You square the characters for that type of irreducible representation to generate the new thing that you can reduce into its components. All right, and then what's important to us is that the transitions occur from that bottom of the diagram, the ground state, to excited states. And it would be way easier to use this if we were able to flatten out this bottom here. And so when that's done, it's just drawn in what's called a Tanabe-Sugano diagram. Japanese researchers developed this method, and it's universal. So one of these diagrams works for any complex under any field strength. But for that to work, we have to have a new variable, which is called the Raka parameter. And we'll talk about that in a little bit. So this is that same D2 configuration. If we kind of look at these side by side-ish, just see how these are connected. Okay, it's in microscopic font here, but this is the triplet T1G term on the bottom, which is this ground state here. And you see we've just flattened it out, right? And so everything is relative to that now. So the first transition we see is to the triplet T2G, which was always the case. So this slope is sort of greater than what appears to be this slope, but that's because it's really the slope between these two lines, which are diverging, right? These two lines are approaching each other, sort of, not really, not slightly, but so anyway, that's this one here. You see there's some lines that curve here, which is kind of an added effect of electron-electron repulsion, which is taken into the Tanabe-Sugano diagram, but not here. So when you have some transitions, I think the transitions, different states of like symbols curve away from each other because they have electron-electron repulsion between the two states, strangely. It's not that important, but it is an effect of this. So along the x-axis here, which was the field strength, you see it's related to delta. Okay, so delta is the x-axis, which is the measure of how far we are away from the free ion term, is a measure of delta, but it's delta divided by this ratio, by the variable b, the Raka parameter. And on the y-axis, it's the energy, okay, which is going to be, you know, the photon energy of our transitions, also divided by that same parameter. So B shows up in both axes, and that's how we'll solve for it, because we actually know the energies of our transitions. We have to figure out where we are on this diagram to figure out what delta O is. So our job is actually to figure out where we are along this x-axis using multiple transitions. And so, for example, if we see transition energies that are here and here, right, there's a ratio between those two. It might be maybe a 3-to-2 ratio or something like that, right? Looks like it's roughly there. And there's only one place on the diagram where that's true, right? If I go really low here, this is like a 1-to-1 ratio, right? And if I go way out here, it's like a 9-to-8 ratio or something. Okay? So that they get like these two lines, you know, relative to the ground state here, kind of approach each other. And if I go like infinitely far away, they're basically the same energy, right? So I'd see one peak now. So if I see two distinct peaks and I know how far apart they are, I can tell where on this diagram I am. And you can do this graphically. This is the historical way to do it, is you actually get out a ruler and you measure the distance of this line to this line, right? And you take that ratio and figure out where you are. But there are better ways, and so we're going to use the better ways. Because people have plotted these lines, of course, and now we have tables of data. This is actually one where you look up a table of data. And you fit it, you find the best fit to your particular points. So let's talk about what to do here, okay? So it's a lot of words, and I just try to be careful in this because this is complicated. I want to have you give you something to read. This is also described in the book, but it's not particularly easy to get a hold of. Okay? So, in general, the octahedral field is the distance, the difference in energy between, it's defined as a different energy between the T2G and EG orbitals. For the D2 configuration, if we think about this free ion term and what's happening over here and what's happening out here, really all of the transitions are representing transitions from T2G directly to EG. So it turns out that all this work is going to basically, we're going to calculate a line with the slope of 1, the slope of y equals x, I should say. There are cases where you absolutely have to do this, and the D6 configuration you'll have to work on later is one of those. But I'm getting ahead of myself a little bit. The ground state term represents occupancy in the T1, the T2G orbitals, but it's the term is triplet T1G. And the next state represents an excited state with a single electron per moment. So the energy difference should be, since we're going from a state which is a single occupancy in EG, and we started with a double occupancy in the T2G orbitals, the wavelength we see, the frequency we see, should be equal to the energy of octahedral field. But in general, it's better to use the diagram and find the best fit of all of the peaks. And there are some cases where the energy difference you're seeing in each individual photon is not the octahedral field. It's just transitions between two terms that are contributing. Okay. Especially when I'm sick. Okay, so we'll do some calculations in a moment here, but I want to show you a different Tanabe-Sugano diagram, which looks quite different. So this is a D6 configuration. And what we see here, we see our ground state is a pentuplet D state. And that comes from, this would be not in the split field like this at all, but it's in a, they're all degenerate. It's D6, right? So we're seeing this as our ground state. So it's a D term because our maximum L is 2. 2, 1, 0, -1, -2. This thing could be anywhere, but it's maximized. Our total angular momentum is maximized when it's in the highest one. So that's a D term. It's pentuplet because of all these unpaired electrons here. There are various excited states. And when we begin to apply an octahedral field to this D6 compound, we expect when the field is very small that it's high spin, and at some point we have a big enough field that it becomes low spin, right? And there's a line, there's a discontinuity in this diagram in which all of these things are connected, but they suddenly change direction because we've now switched over to an entirely different mode of electronic transitions. And also our ground state suddenly changes. It goes from here all the way down, and it becomes now a singlet state, a singlet A1 state. The symmetries here are correlated with this. It's pretty confusing, but A means singly, it's not degenerate, right? It's a single state. And so since these are all occupied, it's all symmetric, there is exactly one state that looks like that. And it's a singlet because everything is paired up, right? So we went from a pentuplet state at high spin to a singlet ground state at low spin, which means the allowed transitions are now completely different. So previously it was a pentuplet to, if we follow it way up here, this pentuplet E, that's a pentuplet to a pentuplet, right? It has to keep the multiplicity the same. But after we go to the low spin state, we go from singlets to other excited state singlets. And so there are 3 of those, singlet T1, singlet T2, and then another singlet T1 up there. So 3 transitions would be possible later. Initially, I think there's only one transition possible for these high spin D6 compounds. So you can see only a single peak. So let's walk through how to do this for one example. Next slide. The cobalt ethylene diagonal complex, very similar to what we're going to make in lab, and you have to solve these very problems. So I'm setting you up for success, okay? So we'll do it, this is kind of shown in the graphical way in these slides, and we'll work some out using the tables that I gave you here in a moment. So the UV vis spectrum looks something kind of more or less like this. It's a couple of peaks. I kind of just generically draw this out here. I show these as wave numbers, right? But you'll read these as wavelengths, and this is where I really wish I had brought my calculator today. But to convert between wavelengths in nanometers to inverse centimeters, you just do dimensional analysis, right? You literally invert the length, since we inverse nanometers if we invert this, right? And then you convert nanometers into centimeters. Okay? So what we would do is we would take 1 over nanometers. It gives us inverse nanometers, and then we are going to say something like there's 10 to the 9 nanometers in there's 10 to the 9 nanometers in a meter, right? And there's 10 to the 2 centimeters in the meter. This is telling you. There's 10 to the 9 nanometers and 10 to the 2 centimeters. And when we're all done, our units are 1 over centimeters. That's the right unit. So whatever, this is, you invert whatever X nanometers you have down there. They tend to be in the tens of thousands, so I kind of just cheat and I take, if I have like a 400 nanometer wavelength, I have a calculator. Okay, invert. Can we do scientific notation? Let's find out.
Sure.
Yeah, close enough. Okay. So this is how it'll look to you. Rather than doing all that dimensional analysis, this is not great. Okay, so if I do 1 divided by like 450 nanometers, right? I'm going to get this fraction here. It's tiny, right? Essentially what I need to do is multiply this by, 10 million? 10 to the 7, right? So I could do that. I could multiply it by 10 million. I don't have an exponential notation here. 10, 1, 2, 3, 4, 5, 6. And I'm going to get something like 22,000, okay? So that's roughly in the order of what I'm seeing in these transitions here. Or I can just know that my wave numbers are almost always for this visible range, sort of 10,000 to 20, 30,000, something like that. So I usually don't do the conversion at all. I just sort of look at that fraction and then write it out. 1 divided by 650 nanometers. This would be somewhere like yellow. This is 15,384 inverse centimeters. I'm showing you how to do it. These are already converted over. We'll convert the other ones ourselves because you will always read these off of the spectrophotometer in wavelengths, not in inverse centimeters. So these are what we're seeing in the spectrum are 2 allowed transitions. 2 peaks, 2 allowed transitions from a single electron configuration, right? So these are just 2 different possible excited states among the many different states that are possible in this crazy diagram, right? They're just different allowed singlet to singlet transitions. Oh, so by the way, it's ethylene diamine with cobalt-3. This is going to be a low spin E6. So we're going to be in this right half of the diagram. We know our ground state term because we have the obviously on our diagram. It's just always the labeled bottom line here. Our job is to figure out where we are along this axis here. And so the first of the transitions, the lower frequency, right, the lower wave number is going to be the first of those transitions. So I draw that with a red arrow here, and the second one is going to be the larger frequency. It's going to go to the second allowed transition. If we were right over here, it would be to this singlet T1 term, and then again to this, whatever it is, singlet E term up here. But it's likely that we're past that little point, but who knows? We don't actually know where we are yet. So how do we go about solving this problem? We have 2 data points, right? We're trying to solve 2 variables. We have just enough information to do it. Our variables are the Rocca parameter and delta O. Okay. The Rocca parameter is an intermediate between the 2. So our 2 different energies here give us a ratio if we divide one by the other. So if we divide the big one by the small one, we get a value of 1.37. So it tells us that our second transition is 1.37 times the energy of our first. And so we have to go along this y-axis here and find the point where this number is 1.37 times that number down there. Okay, and you can do this, like I said, with a ruler. This is like right around here somewhere. It's exactly 1 to 1, right? I guess it would be, like maybe 20 to 40, somewhere in here is where that happens, right? If we keep going to the right, they diverge. Yeah, so we're looking at these 2 points right here. So it turns out if you scan along this axis here, and you try to find where this happens with a ruler, and I'll show you, there's tables of data where we can do this, but if you go around measuring, down here, they're farther apart. I guess this would be 2 to 1, I should say. So somewhere down here, it's 2 to 1, right? Up here, they get closer and closer together. So they approach 1.37 near the end of this diagram in this particular one. So that's at about delta O over 40. So run up from this line and I measure across to the left, I find that my frequency 1 axis here is E over B is for the first transition, if I read to the left, I find that this intersects this y-axis at 38. And if I go up to the second transition and I read to the left, I find that the frequency E over B, which is that y-axis for the second transition, is 52. And these are the two numbers we need to solve this thing. Okay. So this is a super weird process. I don't know if this is happening anywhere else other than this Tanabe-Sugano diagram method here, where you use a graph and you try to fit your position on the graph in this way, where you find the ratio and then find the place where that ratio is true and then read off your two values. So we're reading off, basically we know now that our octahedral field divided by this unknown parameter B is 40, right? And we know that the energy of our transition, frequency 1, which is this number, divided by this unknown right now, B, is equal to 38. And also this second transition divided by that same unknown number is equal to 52, right? But we know what those transitions are, right? We know that E for the first transition is this number, right? Because we measured it spectroscopically. It was our first wavelength converted to inverse centimeters. So the first transition we had was about 21,000, 22,000 inverse centimeters. When we divide that by B, it's equal to 38, and so we can solve for B. This is just a little algebra here, so you take, 21,550 divided by 38, we get B of 570. Okay. We should get the same value if we test it for the other one. We'll do this by hand in a moment here, but I'm giving you sort of a complete worked out problem in the notes that all tied together that we can look back on later. So since we know what B is, we know that delta O over B is 40 because that came from down here. Right? That was where our ratio is fit best, and that's how we read across, and we also read down. So we know what B is, so we multiply B by 40, and we get 40B, which is 40 times 570, which is about 23,000. So 23,000 inverse centimeters is the octahedral field strength. And you'll see it's not equal to either of these two numbers here. In some diagrams it is. It happens to be that the energy of your transition is exactly what it takes to excite you through the octahedral field. But for a D6 low spin complex, it's not true. These transitions, none of them exactly represent that energy, but the combined data does tell you about that field strength. So let's work through one of those using your tables. The last thing we do here today. We'll do another one on Tuesday. Be super fun. So let's do a D3 configuration. I gave you that Sugano diagram near the end of the slides here to look at it. The complex we'll look at is a chromium aqua complex. No, not this one. It's CrH2O4 Cl2 Cl. Chloro. We also have word tetra aqua dichloro cobalt or chromium 3 chloride. Chromium came with 6 electrons, right? We remove 3 of them. It's a D3 compound. That's what we want. There's no low spin or high spin for a D3 compound. What we find when we measure its transition is this. We see a peak at 635 nanometers, and we see a peak at 445 nanometers. So if we invert these lengths, we get inverse length units, which just makes sense only to spectroscopists. And then you convert the nanometers to centimeters, and we can get to inverse centimeters. So 1 over 635 times 10 to the 7, for example, is equal to 15,738. We're going to round these off because what we're about to do is pretty rough, the way we're going to use the table of data. So I think if we round them to 3 significant figures or so, we're going to be good. The frequency 2, which was this, we're going to call this frequency 1. This is the higher wavelength, the lower energy one, so it's 15,000 inverse centimeters. We do the same thing to the 445 nanometer case. Go to that. 1 over 445 times 10 to the 7 is going to give us the higher energy one, which is at 22,472 millimeters. We're going to call that frequency 2. We will order them by energy, not by wavelength. Okay. So we're trying to use our diagram, and if we look ahead in the slides, it's the end of your packet are a couple of diagrams like so. So at the end of your packet is the D3 Tanabe Sugano diagram. And so we're starting the quartet A2G term. These letters and numbers don't matter too much anymore, but what we want to do is make sure we go only to the quartets. So I kind of darkened those lines. You don't actually need this diagram, but I think it's helpful to see what these things are plotting. So the values of each of these lines and each of these delta O values are tabulated in microscopic font in this table. This is just pulled from this giant spreadsheet that I'll post on Tracks if you want it. And I already did all the work we need with this data, which is the energies on this diagram of the ground state, the A2. This is why it's helpful to have this thing. This is the ground state, that quartet A2 term, are all 0 because they're at y equals 0. They are the x-axis after all. The first transition we can see is this quartet T2G. So here's their values, and these values are the E over B values. Okay, so this is the y-axis values. So, for example, at 0.5, which is way down here, 0.5 delta O over B, our value is 0.5. Okay. Interestingly, these numbers are equal. Okay, this gives you a big hint about what's about to happen here. But basically, the octahedral field is exactly equal to this this transition energy. We don't actually have to do any of this work. We know these two slopes are equal to each other. But we'll still calculate our thing out. So the second transitions are some weird numbers, kind of roughly sort of double them at first, and then they approach each other again, right? And our job is to figure out where along this axis here our two values can both exist at the same time, where our first transition or our second transition are in the proper ratio. So if I take frequency 2 over frequency 1, I get my ratio, just the big one over the small one. I find that the ratio is 1.428. This is what I call the ratio of the first to the second, second to the first, I guess. And that's equal to this right-hand column. This is the frequency 2 divided by frequency 1, which is the energy of this quartet T1G divided by the energy of the quartet T2G, second transition over the first. So I'm just trying to find 1.428. So scan down here, 1.428. It won't be exact, but you find the closest one somewhere in here, right? Yeah. It's a case where a spreadsheet is actually kind of just useful because these are complicated formulas. It's very difficult to just mathematically solve these points. It's really easier just to kind of have a lookup table like this. So the numbers we need, I think I use this, the bottom one of those, doesn't matter. So I use delta O over B of 23.2, which is this one right here. Okay. This will be the line that I choose to use. If I use the other one, I'll also get very close. I mean, there's some rounding error here. It's allowed. Okay, so what I need to know are these three values. This is my delta O over B. If you look all the way up, it's delta over B. So it's 23.15. My E1, this is frequency 1 over B, is 23.15. Close enough. And then E2 over B is 32.95. I have everything I know, I need to know. I have everything I need to calculate my answer, I should say. I don't need my table anymore. I just needed it to figure out these three values. So from this line right here, I can solve for B, right? Because I know frequency 1 is this 15,000, right? So basically 15,738 divided by 23.15 is equal to B, right? And simultaneously, it should be the case that 22,472 over 32.95 is also equal to B. So when I calculate those, I get 678. So by the way, this is inverse centimeters, so is this. And this is unitless. And so my answers here are in these energy units. So I didn't tell you what the Rockup parameter was, but it's a measure, they say, it's a fudge factor, right? But they say it's a measure of the electron-electron repulsion. So when it's high, it means that the electrons are compacted into a small region of space, and there's a lot of repulsion. So cobalt 3 plus, or chromium 3 plus is relatively small. This is a pretty high value. Anyway, so when I do this for the second value, I get 683 inverse centimeters. These should agree. If they don't agree, you're in the wrong place on your diagram. You've read the wrong y-axis. They're slightly different, and that's because I didn't perfectly fit my ratio here. So it was close. You might take the average of those. So if I average those two numbers, I get 681. It's not super necessary, but it's nice. It gives you a slightly more accurate result because it's probably between these two. Okay. So now I know my B, so I know this is also true, right? Delta O divided by B is 23.15. So if I take 23.15 and multiply it by B, which is 681, this is unitless, this is in inverse centimeters. My answer is going to pop out in the octahedral field in this energy unit, inverse centimeters. I get 15,000, here's, I'll just round it off, 800. So if you look back, we actually had fields plotted out, these octahedral fields plotted out for some different complexes. And this is in the range of normal for a positive 3 ion with a reasonably strong field ligand like ethylene diamine. If we had cyanide, it would be higher, maybe 18,000. If we had chloride or aqua complex, oh, this is an aqua complex. So this is a pretty weak field ligand, but it is a highly charged metal. So yeah, they go up to sort of 18, 19, 20,000, 24,000 is kind of the high end for one of these small metals. And they go down maybe to 14 or 13,000. So we'll work out another example on Tuesday. There's plenty of other things to ask you questions about on the homework, so I'm not sure I'll ask you a Tanabe-Sugano diagram, but it is important that you practice this. There will be one question on the upcoming exam like this.